Thank you, Daniel, for your kind introduction. My name is Detlef, and together with my colleague Jade, we will guide you through this presentation. Ladies and gentlemen, we will discuss HPAC pad in food, beverages, and biomass analysis. And because we placed the title like applications of HPAC pad in food and beverage, which reminded us of a menu, we thought we should create a menu for today's presentation. So let's have a look at what today's menu has to offer. We will start with a discussion on column technology, sample preparation, and application development. The main course will feature honey, various beverages, meals containing meat, pork, and processed meats. We will also discuss artificial sweeteners, milk dishes, including those that are lactose-free or contain prebiotics. And for dessert, well, we are going to have a sweet summary avec une surprise verte. So please stay tuned. So what that is? Well, you will have to wait until the end. Let's discuss the typical architecture of our sweet sap columns. They all utilize a polymeric central particle, the core, with a diameter of 5 microns, which is monodispersed to achieve a narrow size distribution. The result is a minimal diffusion contribution and sharp chromatographic peaks. The second design aspect is nanosurface particle modification. We sulfonate the central particle and add a significantly smaller second aminated particle, about 0.15 micrometers in diameter. And by combining the positively charged nanoparticles with a negatively charged central particle, we create agglomeration on the core surface. This control over the particle size also affects column back pressure. Chromatography with nanoparticles accounts for high chromatographic efficiencies and selectivities, which enables the separations you will observe. These separations can be performed routinely thanks to the improved design of the sweet sap columns. Now that we understand the stationary phase, let's discuss an essential prerequisite of practical chromatographic analysis: reproducibility. This depends on the stability and longevity of the analytical system. This slide displays 10 consecutive injections of a mixture of mono and disaccharides with different colors indicating the overlaid chromatograms, and you hardly can tell them apart. That's reproducibility. Now, reproducibility must be maintained throughout a column's lifespan and across batches. However, it also must align with the right technology, specifically in our case, AEX or ion exchange, and the chromatographic instrument. This combination requires careful design for compatibility. As noted in earlier webinars, the ALEXYS Carbohydrate Analyzer is optimized for carbohydrate analysis using HPAC pad, featuring a metal-free flow path and the temperature-controlled autosampler for enhanced performance. The Decade Elite PAD pulse interferometer detector excels in stability and sensitivity. And now a private word, having worked as a product specialist in ion chromatography, I find the ET210, the Element Tray 210, atop of the pump particularly impressive because of its capability to highly performant degas eluents with nitrogen, conserving helium and money. This device is simply outstanding. We provide 3 columns: the Antec Scientific SweetSap AEX18, the SweetSap AEX20, and the SweetSap AEX200. AEX means anion exchange, and all are constructed from polymer materials. What makes them versatile? At Antec, we prioritize flexibility with customizable eluents, primarily sodium hydroxide and sodium acetate for HPAC separations, rather than changing columns. The SweetSap AEX200 serves as a universal column, adaptable for various analytical tasks by adjusting elution conditions and chromatographic parameters. This includes isocratic and gradient dilution, as well as the analysis of oligosaccharides and polysaccharides. We utilize various pushing ions, such as acetate, nitrate, and methane sulfonate. Our applications cover multiple markets. The exchange sites of the AEX 200 are quaternary amines, and the unique polymeric design ensures stability across pH and solvent compatibility. Then we have the SweetSep AEX18, an anion exchanger specifically designed to meet the demanding requirements of FDG analysis, FDG, fluid desoxyglucose, as outlined in the USP procedure. Despite the shorter runtime compared to traditional columns, the AEX18 presents a higher resolution for FDG from its byproducts. Then there is the SweetSep AEX20, which is used for analyzing monosaccharides, disaccharides, oligosaccharides, and amino sugars in diverse matrices, including glycoproteins and food. Today, we will observe its excellent resolution for monosaccharides to oligosaccharides. The quaternary and ternary amines as anion exchange functionalities offer unique selectivity for the AEX20. In addition to these columns, we have dedicated trap columns, such as the borate ion trap, which removes borate from laboratory water, preventing carbohydrate peaks from tailing and thus improving chromatographic results. The amino acid trap removes amino acids from samples, and because of that, the borate ion trap is positioned between the pump and the injector, where the amino acid trap is situated between the injector and the column set. Now that we have wrapped up our starter, let's dive into today's main dish. Honey. Honey, as defined by the Codex Alimentarius, is that delightful sweet substance created by honeybees from nectar or plant secretions. It is made of a blend of sugars, water, organic acids, and a few other components. To give you a picture, fructose and glucose make about 80 to 90% of the sugars, along with smaller amounts of sucrose, maltose, and trehalose. The Codex Alimentarius outlines the minimum fructose to glucose content and maximum sucrose content, and it's interesting to note that the fructose to glucose ratio can differ amongst various uniflora honeys. The honey sugar fingerprint can help tell apart blossom honey from honeydew honey and evaluate uniflora purity, where HPLC pad plays an important role. On the chromatogram, you see peaks for glucose and fructose. At the same time, other components are neatly separated on the SweetSep AEX200 using sodium hydroxide at 30 degrees C, and the total runtime for this efficient carbohydrate separation is about 25 minutes. Some adulterants include corn syrup, which contains glucose and maltose, high fructose corn syrup, sucrose, rice syrup, and inulin syrup. This chromatographic separation is particularly helpful in identifying adulterants in honey and provides insights into the melicytose content. Did you know that melicytose can thicken honey and make it a bit trickier to harvest? And just earlier today I learned that melicytose is the most hated sugar by the bee makers because it can harden the sugar so that they might even lose 60 to 70% of their harvest. So, and we can give them an early warning about that in the production of the honey. When checking whether honey is mixed with syrups, you can adjust the method while keeping the call intact. In other words, you keep the SweetSep AEX20 along with a sodium hydroxide, sodium acetate gradient in the instrument, instead of relying solely on a pure sodium hydroxide base element. This approach facilitates the elution of larger carbohydrates based on their degree of polymerization, short DP. We can detect adulteration by comparing the unique fingerprints of the samples. So for example, we created an adulterated sample by mixing rice syrup with honey. The original honey is represented in the blue chromatogram, while the adulterated sample appears in red, showing larger peak areas for the components specific of rice syrup. The rice syrup, that's the green chromatogram, and you see that some peaks are being highlighted with an asterisk to show what we are focusing on. To notice such subtle differences in the fingerprints between the samples, it is crucial to have stable chromatographic separation and good response. The method presented here benefits from the tailored combination of a dedicated ALEXYS Carbohydrate Analyzer with a superior SweetSep column performance. This results in reliable performance, injection by injection, and day by day. So let's continue talking about sweet stuff. Yada, what do you have in store for us?
Well, from nature's sweetest gift to science's sweetest trick, let's explore artificial sweeteners. 3-chloro-galactose sucrose, better known as sucralose, is a unique trichlorinated disaccharide that we can separate using the SweetSep AX200 method, which involves a sodium hydroxide and a sodium acetate gradient, followed by the pulse and barometric detection. So take a look at the conditions here. They are pretty standard, and the halogenation doesn't interfere with the pulse and barometric detection at all. So what's exciting is the sample preparation, which we will cover in the next slide. So preparing beverages, particularly carbonated ones, is all about removing the carbon dioxide from the carbonic acid. So following the flowchart from left to right, we start by taking a specific volume of carbonated beverage and studying it for about 30 minutes. This helps to remove the carbon dioxide from the sample effectively. Once that's done, we dilute it. This is a straightforward procedure we can typically apply for these type of samples before filtration and dilution. Then we move on to the exciting part, injecting it into the ALEXYS Carbohydrate Analyzer. So with this slide, we present the analytical results for sucralose in the orange soft drink for various origins and recipes. On the left, you will find the popular orange soft drink from the Netherlands, and on the right, the same brand but from the US. The left side shows three distinct traces: a low standard, a treated orange drink, and a spiked sample. This confirms the presence of sucralose in the Dutch drink, an artificial sweetener approved for the use in the EU. Meanwhile, the US drink doesn't exhibit any sucralose, but when we spike it, a peak appears, suggesting that another sweetener is being used. So if you're curious about the recipe details, feel free to check online. We discovered that the US drink contains aspartame, which is determined by reverse phase chromatography and UV detection. So, Detlef, what other beverages can we analyze with our ALEXYS Carbohydrate Analyzer?
Well, Yada, there are plenty, and one of the fascinating ones is milk. Lactose tolerance is a fascinating global topic. It highlights how our bodies can handle lactose, whether we can metabolize it or not. Interestingly, different regions have varying levels of lactose intolerance due to historical dietary habits. Typically, we see that lactose intolerance in adults tends to increase as we move from the north to the south, influenced by the availability and consumption of dairy products over the centuries. This trend is more prevalent in the Northern Hemisphere, resulting in lower levels of lactose intolerance in that region. Approximately 25% of the European population and between 20 and 40% of the people in the Northern Hemisphere experience lactose intolerance. Given this, essential regulations are in place to determine the lactose concentration in products labeled as lactose-free or low lactose. So let's dive into how we can do that. And no surprise, we are using HPAC-PAD for the determination. But we won't inject milk directly. We won't inject yogurt directly either. So we will prepare the samples before injection, primarily removing proteins and fat. And how do we do that? Well, we take the sample, the dairy product, and dilute it in water. Then we precipitate the proteins using Carré clarification, and along with the precipitation of the proteins, we simultaneously remove fat. The sample is then centrifuged and the supernatant is collected, diluted with water, filtered, and injected into the carbohydrate analyzer. Let's explore how we determine lactose. The chromatogram displayed here, the chromatograms, displayed here are obtained using the SweetSep AEX200 under isocratic conditions, utilizing a sodium hydroxide-based element and PAD, pulse and barometric detection. Several aspects stand out when examining the chromatograms. First, let's talk about the runtime. It's just 10 minutes. We complete the run and smoothly transition into the reconditioning phase. That means our runtime, as said, is relatively brief. What's even more fascinating is that the chromatogram, especially this standard, clearly illustrates the separation of the lactose epimers, allolactose, lactose, and epilactose. Plus, we can also determine lactulose under the specified conditions. The blue and red chromatograms show us the lactose-free sample after it's been treated, while the blue trace represents the same sample after spiking, and the red one is the original sample after treatment. So this setup helps us to identify the component that we are interested in, or the components more specifically that we are interested in, ensuring that the most essential carbohydrate, lactose, can be determined without any interference. Now, one beverage, milk, now another beverage, beer. Beer is one of the oldest and most popular alcoholic beverages made by fermenting starches from grains, primarily barley. So the brewing process extracts carbohydrates from grains into mono and polysaccharides, which yeast ferments into alcohol. Only glucose, sucrose, fructose, maltose, and maltotriose can be fermented. These sugars affect the beer's strength, flavor, color, and aroma, making the monitoring of carbohydrates crucial for both quality control and nutritional purposes. Analyzing fermentable sugars present challenges due to the presence of non-fermentable sugars and byproducts. Beer also contains phenolic acids and components derived from grains. Unlike GC and HPLC, HPLC pad allows for sensitive detection without the need of derivatization. This slide showcases the combination of fermentable and non-fermentable sugars separated on the SweetSap AEX200 using a sodium hydroxide and sodium acetate gradient completed in 35 minutes before reconditioning for the next sample. It identifies galactose, glucose, sucrose, fructose, lactose, maltose, and maltotriose, while oligosaccharides and polysaccharides elute after maltotriose and can be analyzed with an appropriate gradient. During our exercise, we had the opportunity to test a range of beer samples, including the traditional and the non-alcoholic varieties. The conventional beers were diluted 1 to 100, while the non-alcoholic beer was diluted 1,000 times, and I will have to explain the reason for this on the next slide. We spiked the samples with a standard mix for peak identification, as seen in the chromatogram. Sugar alcohols along with mono and disaccharides elute before 25 minutes, while larger carbohydrates follow afterwards. Now, in order to keep our focus sharp, we decided to exclude oligosaccharides and focus on monodisaccharide in this discussion. All samples contained galactose, glucose, sucrose, fructose, maltose, and maltotriose, with only a trace of lactose detected. Well, lactose is often added to certain beers, like stout, to increase their sweetness and the mouthfeel. In all alcoholic samples and all alcoholic beers, maltotriose emerged as the predominant sugar, concentration-wise, with fructose coming next. Please note the time region between 1.5 and 3 minutes, where several peaks elute, and the first one is likely ethanol. These peaks are characteristic for alcoholic beers and are absent in non-alcoholic variants, which we will explore next. In contrast to alcoholic beer, non-alcoholic beer, which you see in front of you, the chromatogram of which see in front of you, contains a noticeably higher amount of fermentable sugar. One reason for this could be the addition of sugars after the alcohol removal process to boost the flavor. HPLC pad measures the sugar content, and in this refreshing alcohol-free beer was found to be 3.4 grams per 100 milliliters, or 34 grams per liter. Well, and this necessitates the stronger dilution of the non-alcoholic beer. Another interesting difference in the chromatogram is, as we said, the absence of the early eluting peaks around 1.5 and 3 minutes, because they are associated to the alcohol content, and in an alcohol-free beer, that's missing. And now the question is, do we enjoy drinking alcohol-free beer along with the higher concentrations of carbohydrates being added, or do we prefer other non-alcoholic beverages? Fermented beverages and sugars, I see that connection. But sugar and coffee? Yada, what can you tell us about this topic?
Well, Detlef, did you know that coffee comes loaded with sugars naturally? Coffee is one of the most popular beverages worldwide, celebrated for its stimulating effects and many health benefits. Carbohydrates make up over 50% of dry weight of coffee beans, contributing to the aroma. During roasting, carbohydrates react with amino acids through the Maillard reaction, influencing the coffee's color, flavor, and viscosity. High consumption and rising prices leads to food fraud, with beans being adulterated with cheaper additives such as glucose syrups. So, HPSC PUT effectively assesses the quality of both the coffee beans and instant coffee. The corresponding AOAC and ISO methods detail the chromatographic quantification, allowing a maximum carbohydrate content of about 2.5% of glucose and 0.5% of xylose. The AOAC method 995.13 utilizes anion exchange separation with deionized water, followed by the post-column addition of sodium hydroxide. The following slides represent an improved HPLC PUT method using the SweetStep AX20, enhancing detector sensitivity and accuracy without the need for post-column sodium hydroxide. Sample preparation is crucial, as we cannot just inject the coffee beans or coffee powder directly into the chromatograph. 3 preparation methods are outlined in our application notes. The first, for free carbohydrates, involves extracting coffee beans or dissolving instant coffee in deionized water, treating this mixture with an SPE C18 cartridge, filtering it, and injecting it. To measure the total carbohydrates, we employ acidic digestion, followed by filtration and dilution. So during application development, I even investigated alternative extraction methods, including the processing intact or crushed coffee beans with ultrasonication. This highlights the importance of consistent sample preparation for quality results. So this slide shows a typical chromatogram we obtained after preparing our coffee samples. We used the SweetStep AX20 along with a sodium hydroxide and sodium acetate gradient, which conveniently allowed us to utilize PUT without needing to add sodium hydroxide after the column. You can see a clear separation from mannitol to ribose, as well as a noticeable baseline increase towards the end. This rise highlights the need for a rinsing step to clear out the more strongly retained compounds from the column. So the black chromatogram displays the coffee sample, which was spiked. This was to help you identify the compounds based on the retention time. But take a moment to check out the separation of arabinose, rhamnose, xylose, and mannose. It's a great demonstration of the SweetStep stationary phase excellent separation capabilities. So what we see in the green coffee beans, which means a non-roasted coffee bean, sucrose dominates the carbohydrate composition. During the roasting process, the Maillard reaction causes its concentration to decrease in comparison to others. However, all the compounds that we observed in the roasted coffee are also present here. Mannitol, arabinose, galactose, sucrose, glucose, mannose, fructose, and ribose can be seen as well. Therefore, we can distinguish coffees based on their carbohydrate composition. During application development, we were even able based on the limits set by the ALEXYS and ISO, to identify a coffee that contained higher than expected concentration of carbohydrates. Thus, the HPLC PUT serves as a method for detecting and identifying food fraud. So, a good meal typically includes a main dish, which usually contains some protein and is prepared according to chef's skills. The process is quite similar when it comes to the analytical determination of carbohydrates in protein-containing samples. We need skills in sample preparation to make the carbohydrates accessible for the analytical determination. So, what do we do? The samples, pork, chicken, and fish, were treated the same way. They were blended and then extracted with water for about 20 minutes at 60 Celsius degrees. We then removed the proteins and fat from the sample through the Carré clarification, we centrifugate it, and then dilute the supernatant before injection. So this approach enables us to analyze carbohydrate composition in processed food samples that contain meat. Processed food samples came with different sauces in which the pork, chicken, and fish were marinating, adding complexity to the analytical method. So, as discussed, we removed the proteins and fats, diluted the sample, and then injected it. You're already familiar with the process. We always run the sample not only against an external standard, but also apply a standard addition. During application development, for identification purposes, we spike the samples. In the pork steak, we found glucose, sucrose, fructose, and maltose, all in concentrations ranging from gram per liter level. While this is the spicy pork steak, we also examined other examples for fish and chicken, and they all look pretty similar. Sample preparation is crucial for the reliable determination of carbohydrates in complex matrices, such as these. So, Detlef, what else do we have on the menu?
Well, Jade, a lot. Now that we've enjoyed our starter and the first part of the main course, let's dive into discussing milk dishes or baby food enriched with prebiotics, along with how we can creatively use some leftovers. Just to clarify, I'm not talking about doggy bags here. Instead, we are focusing on biomass analysis. We have now reached the part of the menu presentation where we will discuss prebiotics. This encompasses fructans, fructooligosaccharides or FOS, glucooligosaccharides, GOS, and inulin. Inulin is typically extracted from food sources such as chicory root in its native form. Native inulin is a heterogeneous blend of oligo and polysaccharides with a degree of polymerization ranging from 2 to 60. Several grades of inulin type fructans with varying chain length distributions are available on the market. Evaluating the chain length distribution is essential as it impacts both the nutritional and functional properties. To identify the chain length distribution of inulin, one applies a gradient illusion in HPLC PET, and this is what you see on the slide. We use the SweetSap AEX200 with sodium hydroxide and sodium nitrate. Correct. We substituted acetate with nitrate, as nitrate is the stronger pushing ion and allows us to increase the number of eluting species. The degree of polymerization on the eluting polysaccharides is indicated in the chromatogram with a label highlighting DP90. In other words, we were able to elute a polysaccharide consisting of 90 monosaccharides in less than 25 minutes, and that is breathtaking, ladies and gentlemen. This demonstrates the superior properties of the chromatographic column and reflects our deep understanding of the underlying chromatographic and chemical prerequisites. As mentioned earlier, fructans are additives in food and beverages, and to achieve the desired properties, native inulin is processed into more purified ingredients, such as long-chain inulin with a degree of polymerization between 10 and 60. We saw an example of that in the last slide. Or shorter fructooligosaccharides, FOS, with a DP between 2 and 7. The separation shown in this slide was done in the SweetSap AEX200 using a sodium hydroxide and sodium acetate gradient with pad, demonstrating the separation of a FOS standard. So what we see are the monosaccharides glucose, abbreviated with an F, and glucose, abbreviated with a G. So glucose G, fructose F, and followed by GF, a disaccharide, which is not sucrose because they differ in their glycosidic bond. And then GF2, GF3, GF4, in other words, mono to pentasaccharides are eluting off the column in less than 10 minutes. I always find it remarkable to observe the efficiency of the chromatographic separation of the SweetSap columns. Just look at the chromatographic peaks. Needle sharp they are. Let's discuss the quantification of inulin-type fructans as dietary fiber, which is essential for food labeling. Unfortunately, the lack of commercial standards complicates the direct measurement of fructans with a degree of polymerization over 5. Fortunately, there is a method existing that implies enzymatic digestion followed by HPLC pad analysis. This process enables us to assess the sum parameter, making the quantification independent of the degree of polymerization as highlighted in this slide. In the first sample preparation step, all carbohydrates containing fructose and glucose that are not fructanes, so sucrose and other alpha-gluco-oligosaccharides, are completely hydrolyzed. Then the remaining oligosaccharides, including the fructanes, are separated from the monosaccharides using an SPE, solid phase extraction. In the final step, the isolated fructans are hydrolyzed with fructanase into glucose and fructose. The detailed sample preparation step can be found in the respective application note on our homepage, ready for your download. So our homepage is www.antexscientific.com. Once again, we are using the SweetSap AEX200. The runtime is impressively short, with analyte elution including the internal standard in just under 8 minutes. We can maintain the same gradient or switch to specific method for glucose and fructose analysis, optimizing the cycle time. The flexibility highlights our versatility with the same column. And just to recap, ladies and gentlemen, we demonstrated the separation of inulin, short-chain FOS, and the sum parameter FOS after enzymatic digestion using the same column with adjusting elution parameters and chromatographic conditions. That is what I call relatively straightforward. Galacto-oligosaccharides are oligosaccharides composed of a chain of galactose units and an optional terminal glucose units. They are increasingly added as supplement to infant formulas to mimic the prebiotic properties of the human milk oligosaccharides, HMOs. GOS are also presented in small amounts in various other kinds of food and beverages and are very resistant to hydrolysis, to digestion, in our digestive process, supporting the growth of beneficial good bacteria. Currently, the most widely used method for determining total GOS content in food is detailed in the AOSC method 2001.02. This method describes the extraction of GOS, followed by an enzymatic digestion of the oligosaccharides, like seen in the previous slide, into monosaccharides and their subsequent analysis using HPLC pad. We applied this workflow on the determination of GOS and infant formula, as you see in this slide. The separation is again performed on the SweetSap AEX200 using a pure sodium hydroxide gradient. It allows the separation of monosaccharides and disaccharides, starting with fucose through galactose, glucose, fructose, allolactose, lactose, and lactulose. The runtime is about 23 minutes and the cycle time, including the reconditioning time, is about 45 minutes. So, Jare, I think now it's time to talk about biomass, isn't it?
I think so too. Thank you, Detlef. So now that we've completed our starter, we are almost finished with our menu. Except we will need to discuss the leftovers. With a wink of the eye, it relates to the biomass applications we mentioned for today's seminar. So, why do we discuss biomass? As you can see on the slides, biomass, such as wood or carbohydrates-rich chitin from shrimp, can serve as a raw material for developing and producing sustainable energy and pharmaceuticals. On the same slide, you already see what's necessary to achieve this goal: sample preparation. This step is really important because wood paper or chitin can't be injected directly. We need to release the carbohydrates from their matrices to move forward. On this slide, you will find a general overview of the sample preparation process, which starts with grinding and weighing, followed by acidic digestion. The flow diagram shows that we proceed with the neutralization step, and then we get to inject the sample into the HPLC pod instrument after it's been diluted and filtered. Digestion is essential for breaking down the glycosidic bonds, allowing us to form neutral sugars and uronic acids. This process is key for understanding the fermentable composition, which is vital for developing exciting industrial applications. On the right-hand side of the slide, you will notice that the sample preparation and acidic digestion vary depending on the sample matrix. Wood samples require digestion with concentrated 72% sulfuric acid. Chitin is hydrolyzed with 37% hydrochloric acid, and other samples were treated with 250 millimolar sulfuric acid solution. Once the samples are neutralized and filtered, we inject them into the HPLC pod instruments. So the injection of such hydrolysis is shown on the following two slides. So let's start with the analysis of the wood hydrolysis. What we do is we take the SweetStep AX20 and apply a gradient. It begins at 5 millimolar sodium hydroxide, initially ramping to 70 millimolar hydroxide at 9 to 40 minutes, being followed by the shown sodium acetate gradient to elute the more strongly retained uronic acids. Their separation is excellent, and even the separation of arabinose and rhamnose and xylose and mannose in these high ionic strengths hydrolysis, where there is a lot of sulfate and chloride, remains unaffected. So the two black arrows indicate specific points to the gradient applied. The first black arrow points to a hump on the baseline. This is due to the increase in sodium hydroxide in the amperometric cell. This leads to a larger current and thus the hump. The second black arrow points at the sharp spike, which is the column re-equilibration process at which the column, initially being in the hydroxide form, rapidly converts into the acetate form, which releases a higher concentration of hydroxides, resulting in a pH glitch. So, although we use hydrochloric acid to hydrolyze chitin from shrimp, distinct differences arise in the chromatograms of wood and chitin hydrolysis. The absence of specific compounds and the presence of N-acetylglucosamine eluting around 10 minutes. Next, consider uronic acids. Their pKa is about 2, categorizing them as a strong acid. Thus, under high pH, they are completely deprotonated, demonstrating strong retentions as shown in the chromatogram. Therefore, their elution requires a high concentration of sodium acetate or other pushing ions. It's fascinating that the chromatographic performance, peak efficiency, symmetry, and resolution remain exceptional despite the presence of high concentration of sulfuric or hydrochloric acid and anions. This shows the SweetStep AX20 high anion exchange capacity and selectivity for carbohydrates. So I think that concludes our main course, which leads us back to the menu card. Detlef?
Yep. So we are back on the menu card. So we completed our starter, we completed our entree, And now it's time for the dessert to complete our joint meal, the presentation. A sweet summary I promised with avec une surprise verte. So we have to answer the question, what is the surprise verte? What is the green surprise? So the green surprise is what you see on this slide here. It is taken from an article called Metrics for Green Analytical Chemistry by Tobiszewski, which is about the greenness of acids and bases used in analytical chemistry based on the GSK selection guide. And if we zoom into the critical part, the important part for us, we see sodium acetate, potassium acetate, sodium hydroxide, and potassium hydroxide in green. Essentially, these are the elements we use in HPLC PET for carbohydrate analysis, and that is the green surprise. HPLC PET addresses many aspects of a green method, an analytical approach that does not rely on harmful organic solvents or derivatization reagents. It allows for direct injection and detection, saving time while also improving the data quality because there is no need to organize, handle, or train derivatization techniques. That said, the characterization of greenness of acid and bases depend on their environmentally friendly conversion into salts using a simple neutralization process, which is safer for the aquatic environment than using organic solvents. The properties of green. Who would have thought about that? We hope we were able to show you that the combination of the ALEXYS Carbohydrate Analyzer with the SweetSep column set provides you with robust solutions that lead to applications that are guaranteed. Now, what you see here is only a small selection of applications you can find for download on our homepage, www.antechscientific.com. We are proud to show this performance and guarantee our applications. As we wrap up our delightful meal together, we are excited to share the hyphenation of our improved column technology alongside a specialized carbohydrate analyzer. This incredible setup not only excels in separation, but also shines in detection. You will see just how well it performs through its application stability, response factors, and our commitment to quality guarantees. Ultimately, what truly matters is how the analyzer performs in your hands. We hope that the applications we presented today give you a glimpse of the fantastic things you can achieve with our SweetSep columns and analyzer concept. We believe this helps elevate your daily menu, your analysis. So thank you so much for your attention, and we can't wait to answer your question. And I think that's the moment when I pass back the word to you, Daniel.